How to do it.
I like that too.
Maybe it's not about both. Yeah. Yeah. They try to keep on getting. I did on the three.
So fun.
Because I like that, I was like, no, we don't want to do this.
Okay, if you guys can turn to page 7 and 8.
I actually don't have.
Oh, okay.
So we're like, might have 30, 40 people get cancel if they might jump you or something. He's like, oh, say open, say open. That's what we're saying.
Page 7 and 8. I want to kind of go through some of these problems, and it's going to lead into P.3 homework. Some of you guys may have already started on the P3 homework. I want to step through some of the problems in the homework as well to kind of help you get started, so that hopefully you won't have too much homework to do this weekend, because we've done most of P1 and P2, and we're going to get started with P3. If you guys can, actually, page 7, a lot of this is P2 material that we've seen, how to write the equation of a line. So the strategy there is find an ordered pair, or identify an ordered pair, find the slope, and then do point slope form. But I'd like for us to start with page 8. Okay, so if we go to page 8, I want to kind of lead us into function function analysis, or substitution involving function values. Okay. Now, before you guys write anything down here, I'm gonna turn the lights off. Here, still having issues. That'll help a little bit. Okay, so. Okay, so don't write anything down yet, but just kind of want to ask you a series of questions here. Let's say our function is 3x plus 7. Okay. So if I ask you what f of 1 is, you would do what? Plug in 1 for x, right? So you would remove the x. In place of it, you will put 1 in it, right? So okay, easy enough, right? Now, let's say I made the argument more involved. The idea is still the same. Okay. We remove the x. In place of it, if you want to do this, you can leave a reserve spot for that argument, and then we can insert that 3 plus k in. Okay. All right, so how about this? F of x plus h. Same thing, right? Remove the x, put in the new argument. You may have seen this in your homework here. X plus delta x. Think of delta x as its own variable. They kind of delta x goes together. It's one thing. Same process, right? So we are removing something and putting something else in place of what we removed. So we want to make sure that we understand this process, and we don't just think of this as, okay, that delta x, okay, so this is what I see a lot of students do. They take the expression And they just add the delta x there because they see the plus delta x, but that's not how this process works. Okay. So we are removing something in place of it, we're inserting something else. Okay. Now, let's go to this problem here. See if we can build what we need to be able to substitute this numerator. So it says find the value of f of x plus h minus f of x all over h for each of the following functions. Okay. So our f(x) is 3x plus 7. So we know this will insert itself into that expression. But we need to build f of x plus h. And we just did it just now, but we're going to go ahead and just have it here. So again, I'm removing the x. And in place of it, I'm putting my new argument. Okay, so now that I have all my pieces, I'm going to start replacing my numerator and get the numerator out of function expression, or get it out of function notation. Okay, so f(x) plus h, I have a perfect replacement for it. We built that just now. We're just going to follow along. Whatever this expression is telling us to do, minus f of x. All over h. If there's something else we have to include, and what's that? Parentheses, yeah. Parentheses around the 3x plus 7, because this minus means I want to subtract everything that comes after the minus sign. So both terms need to see the negative sign. Okay, I'm just going to go ahead and see if I can clean this up all the way out, distribute all the parentheses, get rid of all the parentheses, combine like terms, and see if we're able to get it down to a more simplified expression. Okay, so this has this means something, okay, but we're not going to get to that until unit 2 when we talk about derivatives. But right now we're just focused on the algebra portion of it. Okay, combine like terms. 3x's goes away, 7 and negative 7 goes away. Three h over h. Now the h's can easily be removed, can be reduced. I'm just left with 3. Any questions with that process? Okay, so try part B, same idea. Build your f of x plus h first, and then you can go to the expression and start replacing the numerator and get it out of function notation. So I just want us to set it up. Let's not worry about expanding and cleaning everything up. I just want us to see if we can get that first step down. Can we make the substitutions correctly, and can we get the numerator out of function notation? For this process, right? We're going to remove something, and then we're going to replace that something with the new argument. So I'm just going to walk around and see if you guys are able to see that and be able to make that adjustment and build f of x plus h correctly. Okay. Yes, got it.
This is good enough, but you want for this is large. It's good. Yeah. Start it out. You don't mind something? Therefore, it's just not good. So first one, I'm still roll out the sheets and it's back to and then I see this was back to the fire. Thank you. Yes, the board. See how that minus sign there? That minus is going to change everything that comes out. Plus 2 minus. Yes, yeah. Just reaching the side. Yeah. Just didn't put just minus. So. Now, I'm just going to pretend like I'm gonna remove the X and things like this. Really should have, do you like chew on one cat? Yeah. Chew on these calculations. All the X's with French girls.
It just depends, like, if I start to.
Now you know where the expectation on it.
So what is the difference?
So I like mine. It's a bit.
Comes from the fact that that's the new argument. Right here. This is saying for every X put in explanation. Right, it's the same thing, right? If I ask you to find out 1, you would insert 1 into all the X's. So if I ask you to have an expectation, you would insert an expectation for all the X's. No, so now that we have everything that we need, we're going to make a substitution into this P now. This and for that, this and for that.
No.
And that cancels out like.
It's gonna take a second. Too long to comprehend.
Okay, so for part B, we have to build f of x plus h by doing something with the x's, right? We have to kind of take away the x and reserve that spot for the new argument. So instead of 3x squared, now it's going to be 3x plus h squared. instead of 2x, now that x is going to become x plus h. And once we have our f of x and our f of x plus h built, now we can make the substitution for what this expression is going to look like. So I need to make the substitution for f of x plus h, which we have here, 3x plus h squared minus 2x plus h plus 1, minus parentheses, the entire function, original function, all over h. Okay, so for now, I just want us to be able to get to that point. You know, we could expand all the way out, but
Do you have to FOIL that first part?
this part right here.
Uh-huh.
Yeah, so if we were to try to clean it up all the way down, we would FOIL, expand, combine like terms, and eventually cancel out h. Okay.
But you just wanted that like long thing right there?
Yeah, but for now, I just want us to be able to, can we get to that point? Can we make the substitutions and get to that point? Okay. All right, any questions with that? All right, let's go to part C. All right, same process for part C. We want to build f of x plus h first. And then piece by piece, we want to substitute those parts into the numerator of this expression. So again, I'm looking at the original function. I'm going to identify the location of the x, remove it, and then in place of it, put that x plus h, which is the new argument value. Any questions with this step here? Now, what we don't want to do is we don't want to think of that plus h as taking the function and then just adding a plus h to it. That's not the same thing. We don't want to do this. Okay, so now let's do what the expression is, what this rule or this expression is asking us to do. F of x plus h. Let's find the what we created for that. Next up, minus f of x. So minus the original function. All over h. All right, questions with that? Okay. Now with this one, I do want us to practice getting to the end. So I think this is I want us to get that practice with merging complex fractions and common denominators. So, but before I move on, any questions here? Do we see how this represents f of x plus h? This is f of x, and then we keep that h in the denominator. Good. All right. So I want to find a way to kind of merge this and try to clean this up a little bit more. But to do that, I'm going to focus my attention on just this numerator portion. So the hope is that we want to try to merge these two fractions together. But if I want to add or subtract fractions, I have to find common denominators first. I have to find a way to get the denominators to match. So I'm going to step to the side here and just focus on that portion. So in order to combine two fractions, I need the denominators to be the same. I need common denominators. So what's a common denominator that's large enough for both those individual fractions to factor into or to multiply into? So these are two distinct fractions. I need both of them to create the common denominator. So my common denominator is x. That's right, x and x plus h. I'll leave it in factored form. It's easier to work with down the road. Okay, is everybody good there? We need both individual fractions to create the common denominator, or both individual denominators to create the common denominator. And now that we have the common denominator, we have to figure out a way to balance each of the fractions, right? So we look at the first old denominator, compare with the new one. What's changed? What's been added? The x. Okay, so because an x has been added from the old to the new denominator, I also need to add an x to the numerator of my first fraction. So 6x would be the adapted numerator for my first fraction. Okay, second denominator. What's changed from first to the second? X plus h. So I need to make that same adjustments with my numerator. So now that I have common denominators, I'm going to merge them together and find a way to get the numerators to combine, or to we can do like terms with numerators now. So this is 6x minus 6x minus 6h over x times x plus h. So what we started here, we're able to now clean up to this point. But remember, that's still all over h, right? Still all over h. Right, so now we can make some progress with the numerator. The 6x's can go away. I'm left with negative 6h over x times x plus h all over h. Okay, I'm still dealing with a complex fraction. Right, got a fraction within a fraction, but now it's a lot easier to work with this piece than it was here with the two terms separated. So now I'm going to find a way to try to merge the numerator and denominator together. And I'm going to take this h, I'm going to flip it up to the top, right? I can always move something from one side to the other if I multiply by the reciprocal. So what's the reciprocal of just h? 1 over h. So that allows me to shift that h to the top, and we know that's just going to go away. So now I'm just multiplying these two fractions together. Do you see anything that can reduce from here? The h, okay. The reason that we're able to match the h's and make them go away is because those h's have no addition or subtraction attached to them. Okay, and because that's the case, we can cancel across multiplication. Now, if there was an h plus 2 or anything that's added or subtracted with these h's, then we can't cancel out. But we can cancel across division, multiplication. So that allows us to clean up to this point. We typically like to leave something in factored form. So, I mean, you can expand the denominator, but this is perfectly fine. Okay, let's see if we can work on some of the problems from the P3 homework. So this is page, I think page 26, 27. And let's start with number 7. Okay, so see if you guys can set this up. Hopefully after we've gone through the last exercise, this will feel easier. See if you can build f of x plus delta x. Substitute your numerators and stop there. Don't worry about expanding all the way through. I just want to see the setup, replacing the numerator and get it out of function notation. Okay, what do we find or discover for f of x plus delta x? If f of x is x cubed, what's f of x plus delta x? Good. X plus delta x cubed, right? I'm removing the x variable, and in place of it, I'm putting that x plus delta x cubed, or x plus delta x. Okay, so let's just replace the numerators out of function notation into an expression form, or into expression values. Okay, we can stop there. I just want us to get to that point. Okay. Technically, we can write out the 3 binomials and expand. I'm sorry?
Why don't we change the bottom?
Why do we change the bottom x? Because the bottom is not x, it's delta x. And delta x is like its own variable.
Yeah, so it's how we didn't change the second time.
That's right, yeah, we did not, we're replacing the x with x plus delta x, but this, think of delta x as an h, or just another variable.
It's also not an f of x either. It's just like sitting there, you know.
Yeah, say that again, Phil?
I said it's not an f of x, it's just x.
Exactly, right, exactly. Delta x, we're only substituting something out of function notation, so it's only the numerator that needs to be replaced. Okay, number 9. Okay, so number 9 is asking for us to make the substitution needed to make it so that f of x and f of 2 can be replaced. And we just want to create a different version of this expression. Okay, so we know what f of x is. That's just the original function. We can insert that in a second. How would I find f of 2? Yeah, replace 2 in for x. Yeah. 2 minus 1 is 1. And 1 over square root of 1 is still 1. So here, I just need to do 2 substitutions. I just need to figure out what to replace f of x with, and then figure out what to replace f of 2 with. Okay. F of x, here's our substitution for f of x. Here's my substitution for f of 2. For now, let's just leave it in this form. That's fine. Yes.
Yeah, I was gonna ask about that too. Or is because it's a family.
We don't, we just want to get this out of function notations. So we only are replacing that sum that's in f of x or f of t. X minus 2 is already fine. It's able to work with the numerator, but we can't work with something that's in a function.
Yeah. One of my teachers told me to think of f of x as y, so just a completely different variable.
That's a good point, yeah. We want everything in terms of x's. The f of x is a different quote unquote variable, so we need to make those substitutions. Okay. Let's see, next 15. Okay, we want to figure out the domain and range for g of x equals square root of 6x. Rather than having to figure out each of the ordered pairs and actually creating a table of values, if we just know something about this function in terms of something that's similar to it, then we can kind of build out and find and sketch a quick graph and figure out the domain and range. So here's what we're going to use. We have a parent function that looks very similar to this one, which is y equals square root of x. And the root 6x is just a transformed version of this function. So I want to show you what square root of x looks like. Starts at 0, 0, and then it rises and it's curves to the right. So root 6x, if you think about transformations here, the 6 is going to do something to the shape of the graph. It's going to make it more, it's going to shrink it a little bit, but it's still going to remain the same shape. So there's not going to be any shift. There's no plus or minus inside the square root. There's no plus or minus outside the square root. So this graph is not going to move in terms of its starting point. And also there's no negative in front of the square root, meaning that there's no reflection. So the graph is going to look a lot like this graph, it's just maybe a little bit wider. But we don't have to know the super specifics because that's good enough for us to know what the domain and range is, right? So domain is how far left to how far right the graph goes in terms of x. So what's the furthest left that the graph starts off at?
0.
Okay. And extends to the right to
Positive
possibility. Okay. It does touch that starting point 0, so we need to put a bracket around that point. Okay. For range, we want to identify the lowest y value and extend up to the highest y value. What's the lowest y value? 0. Highest y value. Okay, 17. Now, you may not know what this graph looks like, but I want to kind of maybe start you off with something that you maybe recognize first, and understand why this graph looks the way that it does. Okay. Now, do you guys recognize? So I'm going to step off to the side here. Do you guys recognize this formula? Okay. What is that the shape of? Circle. Okay, so it's a circle with a radius of 4 and then a center of 0, 0. Okay, so that's just a little bit of context here, but I just want to kind of show you, how we can kind of get to the shape of this graph, understanding where it's coming from. So I'm going to just solve for y here. I just want to show you, if I just solve for y squared is equal to 16 minus x squared. Still a circle. But if I solve for y is equal to, right? I got to take the square root. So what happens when I take the square root?
Plus or minus.
Plus or minus shows up. Okay. Plus or minus square root of 16 minus x squared. It's still a circle, but the positive square root is going to do the job of the upper half circle. And the negative square root is going to do the job of filling in the bottom portion of the circle. So this y equals square root of 16 minus x squared is only referring to the upper dome of the circle. So it's a half circle. So that's where this is coming from. And we know it's a radius of 4, but we can also do this. We can also difference of squares here, 16 minus x squared. Those are both perfect squares. So 4 minus x and 4 plus x. If I solve for x, I get 4 and negative 4. So that tells me the endpoints of my semicircle. So now that we have the semicircle in front of us, we should be able to easily identify the domain and the range. So domain, how far left does this graph extend to? Negative 4. And to the right, range, lowest y value, y value,
0.
0, right? The lowest the graph is going to go is here on the x-axis, and it's going to only extend up to a y value of 4. Okay, let's look at 23. Sorry, let me leave this up here for another second here. All right, 23. Now we have two different expressions. We don't really have to know what the graph looks like. If we can figure out the domain for each of these individual functions, then the domain of the two of them added together is simply the overlap of these separate domains. Right. And the reason why we do that, the reason why it's going to be this is because the graph is not going to show up if it doesn't fulfill both restrictions, right? So even if square root of x can handle a value. If this can't handle that value, then it's not going to show up at all on the graph. So I want to kind of just talk about each of these functions individually. So square root of x looks like this. We know the domain for this first term is 0 to infinity. We know the square root of 1 minus x is going to have it's going to shift over y-intercept x-intercept of 1, but it's going to open to the left because that negative s is going to force it this way. And this has a domain from negative infinity to 1. So what's the overlap? Well, let's look at these numbers here. So we know the domain for the first one is going to go from 0 all the way over to infinity. But we know the second is going to take negative infinity and go all the way over to 1. So now we want to see where do those two domains line up, because if they don't line up, it's not going to show up on the graph. So you see the overlap is simply between 0 and 1. And that's the domain of this resulting graph. Okay, I'm going to skip a few problems here. I just want to go to 81 and 82. We talked about even and odd functions, but we haven't talked about even and odd functions for cosine and sine. So cosine and sine falls into a specific category. So you guys can go to just create space and you can write down number 81. So we know for polynomial, even function, we can identify an even function if basically if all the variables have an even power, right? We know that even function is where the graph can overlap nicely over the y-axis. If I can replace every x with negative x, if I can get that expression back to the original form, I'm now dealing with the even function. Well, cosine is the even function. If you look at the cosine graph, it folds over nicely across the y-axis, and there's a perfect overlap. So what that means is if I replace every x with negative x, that's going to turn back to cosine of x. Okay. So it has the ability to go back to the original function, and there's no changes. Okay. Sine, however, is an odd function. So odd function is like symmetry about the origin. Visually, that means I can flip the graph upside down, and it's like as if the graph doesn't change at all. Okay. So a feature of odd function is if I replace every x with negative x, it's the same thing as if I'm looking at the function and reflecting it over the x-axis. I can basically remove that negative x and put it in front to show the reflection. It also makes it easier for us to work with if it's -1 times sine of x rather than negative x. So those are the two properties we're going to apply as we decide even and odd functions. Okay. All right, so 81. Okay, so what we're going to do is to determine even and odd function, we're going to test it out. Let's just see what happens if I replace every x with negative x. And based off of the results, we can conclude whether the negative will go away completely or whether the negative is going to stay in front. So I'm going to replace every x I see with negative x. Now, we don't know whether this entire function is even or odd, but we do know a portion of it, right? What do you know about cosine of negative x? that turns positive, right? So I'm just gonna make that adjustment. This negative x isn't gonna go anywhere, but I can clean this up a little bit, the second portion up a little bit. Okay, so now that we've cleaned this up a little bit, let's see how this looks compared to the original. Is this the reflected version of the original?
Yes.
Yes.
That negative.
There's a negative in front, right? Imagine x cosine x, the negative cosine x is going to flip it. And because of that, that is the relationship for odd function. That's the origin symmetry there. So therefore, we can conclude that f of x is an odd function. Even though inside this function, the cosine is an even, but overall, this is an odd function. Okay, last one here, 82. F of x equals sine squared x. So another way of thinking sine squared x is sine x times sine x. Right, that squared in that location means I'm squaring the function, and squaring the function means both of them multiply together. All right, so let's test if this is an even or odd function. Let's replace every x with negative x. And what's the special property about sine of negative x individually? The negative goes in front, right? So I get negative sine of x. And same thing here, sine of negative x is individually is an odd function. So I can pull that negative out. But now that the negative is in front, we're free to multiply them together, right? Because it's not stuck inside the function. It's easier to work with now that it's just a -1 coefficient in front. So what's negative sine of x times negative sine of x? Sine squared x. Okay. Let's look at our results, compare with the original. Did anything change?
No.
No. So it's a what? Even function. Okay, so hopefully able to get through some of the homework with you. Finish up the rest of the homework for the weekend. Come up and get your phones. I'll send out a reminder this Sunday for you guys to so that you know that I'll be checking all 3 homework assignments on Monday. Because this is a semicircle. This is a circle with a radius of 4. So if this circle's a circle of radius of 4, it's going to stretch the same distance every way from 0.
Make sure I bring the same problems. Thank you. Every time, like, I can know, but grandma's telling me, like, grandma's the first day of the picture. Send it to me. Send it to me. Have a good weekend.
Hey, Jack, have a good weekend.
Miss Nancy, that was her first year teaching the AP. She's been teaching AP forever. First time.
Which period? Oh, you were in the 4th. All right, see you then. There's no other teacher that you can think of?
I don't think so.
Yeah, if you email him, I mean, I don't know if he, I don't know if he's okay with having 2 TOs for the same
Well, I mean,
class, but yeah, you can ask him and see what he says.
all right,
Okay.
thanks so much.
All right, so. Hey,
Do you mind writing one of my college recommendations?
sure, no problem.
Thank you.
Okay. You can send me a request or not.
Okay.
Okay.